though, that we have for the next 5 lectures, we have guests coming. Next week is a vice provost from Missouri S&T. He'll probably talk a little bit about S&T, but his main focus is just going to be on the various engineering disciplines. He's got a lot to say about that, and so we're excited to have him. And then the following 4 weeks after that, we have guest engineers coming to class. I put an announcement on the Blackboard site listing who they are. I hope you will attend. I know some of you have already earned quite a few points for this class. I hope you will certainly come and pay attention to their presentations. There's they'll have a lot to say about their work, and I always ask them to say a little bit about what school was like or what it was like becoming an engineer, and then hopefully they'll say some things about their jobs. So look forward to that. Today's talk is dealing with several kind of unrelated topics, 3 unrelated topics. First, enrollment. I guess there's sort of a theme here, which is engineering classes. You might call this the engineering classes presentation. First, you're going to be signing up for classes. I have a few comments on that. Then I have some comments that maybe something's pretty interesting. Some Engineering 101 textbooks really go heavy on this subject of physical analogies. I'm going to say a little bit about it because I think it's interesting but not crucial, but it does bear on your studies a little bit. So I've got a few things to say about physical analogies between different areas of engineering. And then finally, with what time I have left, I'm going to talk about graduate school, what it's like, and why you need to know some things about it. All right, so first, a few things about the freshman level courses. You'll be signing up for classes, and one thing that's often important early on is if you're choosing between, actually I could probably put history on that list too, history, poli-sci, economics. It actually is kind of nice to know where you're transferring to. The different schools have different rules. I used to always say, take economics, then you'll be safe. But it's not quite that simple anymore. For instance, civil and mechanical engineering students going to UMKC shouldn't take economics because they have put economics into a special engineering class that only they offer. And so you wouldn't want to take economics if you're a civil and mechanical engineer going to UMKC. However, if you're going to Rolla, almost everyone takes economics. So it kind of depends on what school you're going to. Chemistry 111 is required for pretty much every engineering major. Some of the majors allow biology instead. That's an option for you. We're fine with that. We would accept biology in place of chemistry for the associate's degree, but most engineers need to take Chemistry 111. Some of them take Chem 112, but most do not, like the civils, the mechanicals, the electricals. None of them actually require Chem 112 at the university. So the people that would take it are people that are more in the science areas of engineering. Chemical engineering, obviously, but some of the others, biological engineering, environmental engineering, some of those are likely to take Chem 112, but most engineering majors do not. Calculus 1 and 2 are considered freshman courses in engineering program. You've completed the traditional freshman year once you've completed Calculus 2 and Engineering Physics 1. Though a lot of students do wait to take Engineering Physics 1 until after they've completed Calc 2. After you've completed Calc 2, you could either take Calc 3 or differential equations, the way we have it set up at our college. And then you could take Engineering Physics 1 afterwards. The problem with delaying Physics 1 until after you've had Calc 2 is that it often has, unless you're a part-time student, it has the potential to push back your graduation date. So the normal plan is for you to take Calc 2 and Engineering Physics 1 in the same semester, but a lot of students rush, get their math done fastest, get that done, then do their physics. If you're taking less than, say, 16 hours a semester, that might work just fine for you. But if you're taking 16 hours a semester, you're trying to keep a full load and get done in 4 years or so, then that might delay your graduation. So you'd probably want to take Calc 2 and Physics 1 the same semester. Typically a computer programming class, but not all majors now require computer programming. So that's another thing to look ahead a little bit. For instance, the Rolla Transfer Guide lists on the back side of this Rolla Transfer Guide that they put on their website for our college, they list first what you should consider taking with us, and then on the back side of that they list all the majors and who needs a computer programming class, who doesn't. For example, civil engineering used to require a computer programming class at Rolla, but now civil engineering at Rolla does not require a computer programming class. So that's the kind of thing you have to watch for. If you're going to civil engineering at UMKC, though, they do require computer programming. Their requirements in the first 2 years are identical to the mechanical engineering requirements. Generally, if you're going to civil or mechanical at UMKC, you can take almost everything we offer in engineering because almost everything counts usefully towards their degree. Another note, I wanted to say a little bit more detail about these programming classes. Engineering 104, for those of you, some of you are in it right now or have already had it, but those of you who have not had it, you should know that it's probably one of our most advanced freshman courses. If you have programming experience, you're good at programming, this class is no problem. You could take it the same semester you're taking Calculus 1. If you've never programmed at all, that's fine, but the class is going to be harder for you. It might be worth it to wait a little longer until you're a little bit more advanced student before you take that class. Another course, this is a course you could take while you're taking college algebra or trig or anytime after. Engineering 113. This is a great course designed exactly to match Rolla's IDE 20 course. That's why we started teaching this course. It's a freshman design course to get you a little flavor of what design is like. Ms. Flum teaches that class, Mrs. Flum, because she's been through a lot of that stuff in her coursework, and she teaches a lot of the design aspects, teamwork aspects. That's a great course to take. Early on, you meet other engineering students, and it's definitely a course, if you're planning to go to Rolla, it's definitely a course you want to get out of the way early on. You don't want to take that down there as a junior with a bunch of freshmen, so better to take with us. It also transfers to UMKC engineering, but you have to have this class along with Engineering 113 to get credit for their 3-hour freshman orientation course, CE 111. It's the course they all take. All right, but mainly I want to talk about the sophomore courses. First, the non-engineering courses, Calc 3, differential equations. Clarify a point about differential equations going to UMKC. In the civil and mechanical engineering department there, they will accept that towards the differential equations graduation requirement, even though it's not the same course as differential equations at UMKC. So if you take differential equations with us, it doesn't count identical to differential equations at UMKC. There's no real match for their course because it's a junior level course at UMKC. But the civil and mechanical engineering department at UMKC accepts our course as the differential equations requirement, which means you wouldn't need to take it after you transfer. So it's essentially the same unless you decide you want to be a math major or a chemistry major. Those majors have to take differential equations at UMKC, but if you're an engineering major, then you're fine taking our differential equations. Engineering Physics 2 is a course that almost every engineering major takes. I think every engineering major takes. Organic Chem is a class we offer, but that's there for it's an option we offer for the engineering associate's degree. We put it in there for the chemical engineering students and other students who have to have organic chemistry. Most engineering students do not need organic chemistry, and so you wouldn't want to take that course because even though it'll help you towards the associate's degree, it's not going to get you closer to your bachelor's degree in electrical engineering or your bachelor's degree in mechanical engineering. So only take organic if your bachelor's degree requires it. That'd be my recommendation. All right, so most of my focus as a teacher at MCC is on these classes, as is Mrs. Flum's teaching. We focus on the sophomore level engineering courses. We hope that you'll take as many of these as you need for your bachelor's degree. In fact, I would almost encourage you to consider taking extras of them if you have the time. Our prices are pretty darn low, and these are the types of courses that every engineer used to take. What's happened over the last 10 years or so, maybe 12 years, is that the organization that makes up rules for engineering, it's called ABET, they really opened up the options for universities to change change the way they do their degrees. It used to be that they mandated that all engineers would take most of these classes. When they changed the rules, some of the departments started cutting out some of these classes and made it so the students only took specific classes in that department. So like civil engineering at UMR, or S&T, they took out a lot of the basic engineering and just put in straight civil engineering courses, which means you don't take as many of these as a civil engineer as you used to. And that's just an example. So the thing is that when you want to become a professional engineer, you have to take the Fundamentals of Engineering exam. And you have to pass that exam just to start earning credit towards your professional engineering license. That Fundamentals of Engineering exam is essentially these courses. And if you've had a good, rigorous treatment of basic engineering, the Fundamentals of Engineering exam is easy. If you went into a department that didn't require any of these, or very many of these, every department requires at least one, I think, but if you went into a department that hardly required any of these, and then you get onto this FE exam, you never even had a course in the subject, or maybe you just had a quick survey course, you're going to have a lot of trouble passing that test. And so it's nice if you get this good fundamental understanding of engineering. For that reason, and in my topic about connections between the classes in a second, we'll tell you another reason why you should consider taking some of these, even if they don't actually check off a degree requirement in your bachelor's degree. I should mention one other thing. These are all calculus-based classes. If you happen to have gone to a school, maybe a different university than the ones that have the ABET degrees, and you took a course with one of these names, but you hadn't had calculus yet, or you hadn't had calculus-based physics yet, then the university is not going to recognize it. So you might have a class called dynamics, or you might have a class called mechanics and materials. They are offered to the technology programs. But if you haven't had calculus and calculus-based physics before you take that class, if it's not a calculus-based version of these courses, universities will not recognize it, and you'll have to retake it at the university, or take it with us, because we offer the calculus-based versions. I want to clarify this class, Engineering 215. This is one class that you could take pretty early on because you don't have to have engineering physics for it. You only need Calculus 2. It is a calculus-based statistics course. It's a pretty tough course because it's a sophomore engineering course, and so it's one you'd need to take pretty seriously. And it's also online, which I do videos through this mechanism for that class, and then we use the Blackboard site a lot. The thing about this course is that it was designed because S&T talked to us about 6 years ago, said, hey, you really ought to consider offering a statistics course. And that had kind of crept up on me because I didn't realize how many different degrees at Rolla required this statistics class, a calculus-based engineering statistics course. It's a really neat course. I love the course. There's 4 flavors of it at Rolla. Those are the 4 things listed there on the screen. And this course that we teach will count as any one of those 4. So whichever one of those flavors your department offers, this one counts for it, because you're only allowed to take one of those when you get down to Rolla. So that works the same for us. Now, if you're planning to go to UMKC or some other school, you need to check into it. UMKC, Mechanical and Civil Engineering, will give you 2 credits of the 3 that you need, which means that if you take our course, you'll still need to take 1 hour, a special 1-hour course at the end of their course, which they've designed just for that purpose. For students who've had some statistics and still need that one last hour, you'll join the course in progress. Okay, so thermodynamics, I just want to say a quick little introduction about what these classes are. Thermodynamics is about the behavior of fluids mostly. Heat and heat transfer and work are major subjects. You do have to have Engineering Physics 1 first. We teach it at Maple Woods in the spring, Longview in the fall. This course is designed to perfectly match the mechanical engineering version of thermodynamics, but the chemical engineering departments at both Mizzou and Rolla accept it also. So even though there's a special chemical engineering thermodynamics class that chemical engineers take, this class counts as that, or it counts as the mechanical engineering version. So chemical engineers should consider taking this class. Engineering statics is a wonderful course. I was amazed after I took this course. It just changes your view of the world. It's what any great engineering class should do. Statics is really great in that way. It seems kind of dull at first. Why things don't move might be the subject of statics. Right? But when you look at structures from then on, when you look at bridges, you look at a vehicle, you look at a tree, anything you look at after that, you're going to see it a little differently after you've had a good study of statics. It really changes your perspective of torque and moments and forces and how things stand up. And it's a great course. And it's also required for 2 of our other courses. You have to take statics first, and then you can take dynamics, which is, it's natural to understand how things don't move before you study how they move. Dynamics is really interesting because it's essentially the same content, a lot of the same content as what you do in the first half of Engineering Physics 1. But you go into more depth, you tackle much more difficult problems. Very interesting course. It's probably one of the hardest courses we teach at the community college because it's got, it's just the nature of the physics. It's got a lot of math and a lot of physics in it, and you have to combine it together to solve these problems involving motion of objects. Rigid bodies, essentially, it's what it's all about. Wonderful course, of course. I essentially majored in dynamics when I was in grad school. Circuit analysis is a course I teach in the summer at Penn Valley, Longview in the fall. Requires Physics 2, so this would be one of the last courses you could take with us. That's one of the reasons we offer it in the summer at Penn Valley, so maybe you could grab it before you transfer to the university. Or we often have students come back and take it later. One thing that's kind of interesting to me is that I often have civil engineering students taking that class as their last class to graduate, because it's not a prerequisite for anything as a civil engineer, but you do have to have it to graduate. And what I find is if the civil engineers wait until they're seniors to take it, by the time they're seniors, they're excellent students who've been through all this other stuff. They have no trouble taking it. You'd think the civil engineers would have trouble with circuit theory, but actually, because they're often taking it when they're more advanced students, they do really well. If you're going to Rolla, for the last 20 years, they've had this rule for all transfer schools. I love this rule. It's really great. It keeps me in touch with the electrical engineering department at Rolla. The rule is that if you're going to get transfer credit to Rolla for my circuit theory course, you have to pass their final. And so what happens is they fax me their final. I give it in place of the final I would normally give to the students who are going to electrical engineering or computer engineering at Rolla. You'll take their final, I'll photocopy it and use it for your grade in my class, and then I send it back to them, and they grade it. And if you pass it, then you can earn transfer credit for my circuit theory class. It's really nice because it keeps me in touch with their department, keeps me in touch with their standards. And so that's a rule, but almost everyone does well on that test. I've hardly had anybody fail the test, and only a few students, generally students who were very, very nervous or just weren't as prepared as they should have been. Almost everybody's passed it. All right, so then there's this other course, Engineering 240, which is, again, another course you'd have to take near the end of your time with us. One little trick about this course is that for civil engineers, this is a core second semester sophomore course. So ideally, you would take it your last spring semester before you transfer in the fall. If you transfer to a school in the fall and you haven't had this course, you're going to have to take it immediately when you get to the university as a civil engineer because it's the prerequisite for other classes, and it might actually kind of mess you up if you haven't had it. So take this course in the spring if you can before you transfer. We do offer it in the fall at Penn Valley for students who are off track. But get it out of the way as soon as you can. You have to have statics first. UMKC does offer this class in the summer to help out students who haven't been able to get it in the spring. So there's that option. If whether you're going to Rolla or UMKC, you could maybe take this course with UMKC in the summer to make sure your fall semester is not messed up. Whoops. This is not really my area. I'm not as familiar with the technology programs at the BTC and at Longview, but we do have a lot of great options for you to consider. Of course, some of you are majoring in these areas. Those areas are great for getting your 2 years and getting out and getting some work, or transferring to, say, CMSU or Mo West. There's programs that accept our transfer credit from these departments. These are not ABET accredited engineering degrees, but they get you into the engineering workplace. They're valuable background. A lot of engineering students should consider taking some of these. The only thing you got to remember is that it's not going to count towards your degree. There's probably nothing. There's very few classes that actually apply, because all the engineering classes are all calculus-based. They're all kind of brain work, not a lot of hands-on. These classes are a lot more hands-on. You might enjoy them a lot, and there are important information in there if you know where you're going to specialize. For example, if you want to be an electrical engineer, you really need to have some experience with electronics and with computers and all the different things that go around with electrical engineering, radios. There's all kinds of things you could be getting some background in if you want to be an electrical engineer, even though a lot of that stuff you would study isn't going to count towards your electrical engineering degree. It's just sort of considered to be life skills or hobby skills, but you really need to have that knowledge if you're going to be effective as an electrical engineer. And the same would be true for any of the other disciplines. So we have these classes. You should look at them carefully. Maybe if you really know where you're going to focus, you know what you're going to major in, you know what kind of work you want to do, then there's probably some classes there that would be very helpful to you on your resume, give you some good background experience. So take a look at those. For example, we've got electronics and circuits at the BTC, HVAC. Someone who knows they're going to be a mechanical engineer going into HVAC, we've got classes in that. We have machine tooling classes, for mechanical or civil engineers. A lot of CAD stuff, a great CAD program you could work on, get some CAD background. Even if you're not going to be doing a lot of CAD as an engineer, it's a great skill to have. And then there's an applied statics and mechanics. Now, the applied statics and mechanics is an example of one of those courses that has the same name as our mechanics and materials. It's a good course, and it applies towards some of our degrees, but it doesn't apply towards the engineering degrees. Longview has the automotive program. Some of you would learn some interesting skills there, some helpful skills. And they've also got the surveying program or the engineering degree with a surveying emphasis that you could look at if you think you're going to be doing civil engineering around surveying. Have a note in here about having a plan. You should plan what courses you want to take each semester. We have advisors at each campus. You could bring your plan to them. You say, I want to graduate from this university with this degree. Here's my plan. You know, how am I doing? You can work with your advisor. You should expect your advisor to use the information from the university you're planning to transfer to. And if anything's not clear, they can email me, talk to me about it. But your advisor and you need to be looking at what the university has to say about this. They're a crucial partner in the transfer arrangement. The other person you can talk to is me. I'm happy to look at your plan. If you have a semester by semester plan, remind me what you're majoring in, what school you're transferring to, any other details like how many hours you can take per semester or anything like that, what campus you can be at, night school, only day, whatever. If you send me that kind of stuff, I can look over your plan with you and maybe have some suggestions. I'm one of the people that helps write the schedule of offerings, so I know what's coming up. You should also visit the university and talk to your specific department, talk to the admissions people at the university. We have these transfer agreements with several universities in the area, but it's still always good to talk with the department advisors. All right, so that's classes. Then I've got this other topic which seems a little different. I don't want to belabor the point. I don't want to spend too long on it, but it's really kind of fun to think about, and it's related to your class choices. The question I'm asking here is, why is it that one type of engineer with only a few extra courses can begin graduate school in most other types of engineering? So for example, if you've got a degree in mechanical engineering and you decide, I'm going to get a master's degree in electrical engineering, you don't need to go back and get an entire bachelor's degree in electrical engineering. You've already got your bachelor's in mechanical. They're going to make you take a few extra classes, and some of those extra classes will actually apply towards your master's degree, even though they're undergraduate electrical classes. You can take some of those will count towards your master's, and then you'll take some master's classes in electrical. On top of that, you get your master's in electrical engineering. So how can that be? Okay, so all the disciplines have a common core. Everybody takes calculus, physics, some basic engineering classes they have in common. Any other thoughts on why? At the distance sites, you should just shout it out, please, or quietly mention it. Okay, well, there's a really interesting aspect. So there's certainly some common things. Engineers have a certain way of thinking. That way of thinking transcends the disciplines. The society, in fact, looks at you as an engineer first, and a specific type of engineer second. So there's a couple reasons, but there's actually something more. Engineers think logically. They have good problem-solving skills, but there is maybe something else involved here, and that's the subject of analogies. You might think this is an amazing fact, that physical systems are analogous. I'll go through a couple quick examples of what I mean by that, and I ask, is that amazing or not? It's not especially amazing. It's interesting, it's useful, but it's probably just what I call a mathematical artifice. It's the way we do math to solve problems, that when we're studying circuitry and we're studying resistors, capacitors, and inductors in a circuit, and then we go, and now we're going to go to a mechanical system, and we're going to study springs and masses and dampers, that there's this incredibly close link between the math and the physical properties. Like mass might be analogous to inductance, which are totally physically different things. Current might be related to velocity. Those, the analogies there are interesting. They're helpful. It's not physically, it's cool, but it's not physically all that crucial. Here's some examples. Like I said earlier, some engineering introduction books really go to town on this subject. I don't think it's worth that, but circuit analysis, thermal systems, fluid systems, mechanical systems, totally different physics. All those are different physical arenas. You're going to study some of those. If you're a mechanical engineer, you're going to study all of them. It depends on your major, how many of those you study, but there's a lot of analogies between those areas. Whoops. For example, we've got circuit analysis. You learn Ohm's law, V equals IR. For capacitors, you learn that the current is the time derivative of the voltage times the capacitance. You have voltage and current sources in circuit analysis. When you go to a thermal system, you have an equation for heat. Q equals the what's called the specific heat, or it's actually the well, I'll call it the specific heat times the mass. That could be called the thermal capacitance. Heat transfer is thermal capacitance times temperature difference. The temperature difference is analogous to a voltage difference. The heat transfer is analogous to electrical charge, or maybe current, if it's heat transfer rate. And there's something called thermal resistance, which is it's the reciprocal of the thermal conductance. And it's very similar to resistance of a resistor in an electrical circuit. The heater, something like a heater that acts like what's called a current source in circuit theory. So heat is analogous to charge, heat transfer rate to current, temperature difference analogous to voltage difference. That's just one of the many. I've got it here for fluids. For fluids, you have something called a fluid capacitance, which is related actually just to the surface area of the vessel. You have fluid resistance, which is basically anytime you have a pipe or a valve, there's a pressure drop, and that pressure drop works just like a resistance of a resistor. Pumps create a pressure increase. That pressure increase is the same thing that a battery does. It causes a step up in voltage. Pumps are analogous to voltage sources or batteries. So there's another analogy between fluids and electrical circuits. And mechanical is probably the most famous one. You have Newton's second law. You have that the spring force is proportional to how far the spring's been stretched. You have damping force from dampers, and that's proportional to velocity difference. It's a very impressive analogy when you do that. It's easy for people to grasp this one because they're used to the dynamics from their physics studies. And then when you want to learn circuits, it's actually very easy to understand circuits in terms of the mechanical analogies, if that suits you. But there's something kind of suspicious about this when you notice there's two separate ways you can do it. You could make current be analogous to impulse, an impulsive force, which is like a kick or a thump. And you can make voltage analogous to location, or you can make voltage analogous to force. In fact, in physics, they talk about the electromotive force. You can think of it like a force. And current is analogous to velocity. The fact that there's two separate methods here shows you that there's actually no physical significance to what we're doing. It's just a math thing, but it's still very helpful. And if you've studied a lot of circuitry, it's very easy to grasp fluids, and it's very easy to grasp mechanical systems. So that's the answer to the question of why can you go to grad school in a different area of engineering than the one you focused on as an undergraduate, because it's not just this one straight path where you're very different from everyone else. There's a lot of connections between the majors, and one of the reasons is that we all use kind of the same math, and that math can be used with different physical systems, and the intuition you gain working in one area will quickly translate into another area. It's another reason why you should take extras of those basic classes. Those sophomore level engineering analysis courses will prepare you for any major, better prepare you for any major. Even if the physics is a little different, the idea is good. It also, there's one other thing that answers this question of, well, why am I taking this? I want to be an electrical engineer. Why do I have to take statics? Or I want to be a mechanical engineer. Why do I have to take circuit theory? Right, or whatever, that kind of stuff, right? You want to know an answer. Well, this is part of that answer. The more of these basic engineering courses you study, the better you'll be as an engineer, regardless of what specific physics you're dealing with. And you never know, you may end up doing some of those anyway. All right, so that brings me finally to the subject of graduate school, which I could talk for a long time about, but 20 minutes is probably about right for this class. I'd be happy to talk with you more about it by email or whatever if you have questions. First, a little outline. Why do you care about graduate school? Why go to graduate school? A little bit about the general types of degrees in graduate school. And finally, the technical, well, specifically then some technical degrees. Since I have a master's and a PhD in the technical area, it's easier for me to talk about those, so I'll focus on those. And then considerations when choosing a technical graduate school. All right, so why do you care? First, some of you will go to grad school, of course. Hopefully a lot of you will go to grad school someday, but certainly some of you will. If that's one of the reasons, you can start getting prepared, start thinking about it a little as you go through your bachelor's degree. Another thing is that when you go to the university, you're going to be in an environment that's driven by graduate school. Universities are focused on graduate school. That's what they do. Their business is research, mostly. You're probably going to a research university. That's what they do. They do research. They bring in money to do research. That research pays for their graduate students, pays for their faculty salaries, it pays for their laboratories. Right. Undergraduate teaching is part of their mission, but it's a smaller part of their mission. And so understanding graduate school might help you to better thrive as an undergraduate. In fact, you might get undergraduate research. Undergraduate research used to be unheard of when I was going through school. It was funny to think that an undergraduate might be able to do research, but now they've totally reversed on that. Nationwide, they're trying to get more students to go into grad school, and they know that if they expose these undergraduate students to research while they're undergraduates, a lot of them will catch the research bug, and they won't be able to resist graduate school because it's really a lot of fun to do research. It can be very exciting, but if you've never been exposed to any research, you might just go out and get to work at some company rather than stay around and get your master's degree or maybe even your PhD. Another thing of why you might care, even if you never go back into school after you get your bachelor's degree, you have a good chance of ending up working with universities. University mission is often to help companies. Your company probably doesn't have the resources to do experiments, or a lot of experiments. They're not going to. They might have some idea. They might have some trouble. A lot of times, a company is able to work with the university to give the university this research work, and it's a win-win situation. The company learns the facts about what they're dealing with. The people at the university are able to maybe get some research dollars from grants because they're working with your company, and they're also able to get some publications because that's what also drives universities is publishing papers on their experiments, on their research. And so by working together, the university with the company, both sides win out, both sides gain things. And the labor is done mostly by graduate students who are extremely cheap labor because they're trying to make their way, trying to get their degree, get their master's or PhD degree. They're trying to get their publications. So they're going to work very hard to do that research to make a name for themselves. So it's a win for everybody. All right, so that's some reasons why you ought to learn a little bit about grad school. And then why go? Why personally do you want to go to grad school? There's a couple reasons that are pretty obvious. Furthering your education. The bachelor's degree is nice. It teaches you a lot of things, but many of you will find that you have more questions by the end of your bachelor's degree than you started with. It's opened up your mind to a whole lot of ideas, a whole lot of questions. You've seen all this stuff. In fact, bachelor's degree coursework is kind of like a race. It's kind of sad. We throw so much stuff at you. We hope a lot of it sticks in your head. But by the end of it, you're thinking, wow, that was so much. And you probably haven't had time to absorb it all. You go to graduate school, you can really take the time to focus on these concepts and really increase your overall understanding of engineering. And so, or some other subject, maybe business or whatever, but you can definitely improve yourself. And that's useful. It might be that you don't have a job right away, or maybe you're not happy with the job offers you've received. Staying around for a master's degree will give you more leverage into the job process. Maybe a lot of companies will automatically give you more money if you've got a master's degree. It's probably not enough to pay for itself just in that. It's a small amount of extra money. If you had been working for those 2 years, the extra money might not pay itself back. It's hard to say, but it could give you all kinds of opportunities. It could end up paying off many times. It really depends. It's kind of a gamble in that sense. So don't. It's not a guarantee of extra money, but it's certainly a guarantee of better job offers and a better understanding of your field. So it can be very worthwhile monetarily, but it's not a guarantee. Fun. I loved grad school. It was so much fun, it almost felt hedonistic. I really enjoyed learning. I didn't realize how much I enjoyed learning until I was a junior at Rolla, and at some point I started thinking, man, this is really neat. All these facts, all this great research, all this interesting stuff, it's really starting to open my mind. And I felt like by the time I finished, I still had so much I wanted to know. And so that was great. When I went to UT, they had 14 different libraries on campus. All these different departments had their libraries. You could go to these libraries and you could study these works, and it was overwhelming. And I could, you could just spend all week doing that. So every week. All right, a little bit about some of the different options. Some of our guests have had MBAs, either in past years or this year. It's not an uncommon choice for engineers. A lot of engineers end up working as managers. It's very common after it might be right away you're going to do some business aspects and a lot of budgetary things, but within 5 to 10 years, most engineers move into some kind of management role. And so the problem is a lot of engineers have had no formal training in business classes, and engineers are pretty good at picking stuff up and learning things on their own, but it's really best to hear it from the experts. So a lot of engineers will go back and get their MBA if they can see that management is in their future. They'll do it at night school, they'll do it online or whatever. Their company will often pay for it, but it's worth it to them. So a lot of them do it. And it probably doesn't make a lot of sense though right out of school, because to be an engineering manager, to be a good engineering manager, you really need to understand your stuff. You need to understand the business, and that comes from the hard work of being an engineer and doing the design in that area, working with the people that are really doing it. Then you can move into higher management and start applying these management skills. It may be worth it to become a PE first. That'd be a really good combination, having a professional engineering license and an MBA. It's maybe not required to do both, but a PE probably is your highest priority right out of school rather than an MBA. Had some people be law degrees. There's a presentation, I believe, in this group of presentations from a patent attorney who's got an engineering degree, and you might enjoy watching his presentation, but that's certainly an option. Also, some engineers end up working as expert witnesses. It's a pretty niche area, but you can be called to testify all around the country in trials about products that have gone bad or whatever, and you'll be the expert witness testifying on the facts of the item. Oh, patent attorney. I forgot to mention, the patent attorney. We've actually got some of our students from Longview are working in D.C. for the patent office. They're engineering graduates from Rolla or Mizzou, and they ended up getting jobs in D.C. doing patent work. All right, so that's some options, but let's focus on the technical degrees because that's more what I'm familiar with. There's typically two options for master's degrees at graduate schools if you want to get a technical master's in engineering or a science. You can either go with hours plus a thesis, or you can just go with hours. A thesis is kind of like a big book report. You're not really doing terribly original research. You're essentially summarizing a lot of other people's research and maybe putting your own little twist on it, but you're not doing a major research effort. It's still probably the biggest thing you've ever written, but it's not really all that overwhelming. So a thesis is not that big a deal, but it's something that is getting you into the research area. You're studying a lot of other people's papers, you're putting it all together, documenting what they've done, maybe putting in a new twist, or maybe you've got some twist on an experiment, or maybe you've replicated someone's experiment. But it's quite a reasonable thing, and most universities would prefer you do that over the other option. The other option is just take a bunch of classes, but you're not really contributing to the research mission of the university if you're just taking classes. So that's why they prefer you take the thesis option. It's one of those things that kind of depends on your perspective. If you're going to school and you only have X semesters, you're probably going to go with the hours option. That's what the Air Force people did when I was at UT Austin. We had a bunch of Air Force service people who were active in the Air Force. They were paid by the Air Force to get their master's degree, or actually one of them was getting his PhD in my aerospace engineering department. And for the master's degree, every one of them picked hours rather than the thesis, because with the thesis, you're just not positive when you're going to get done. If there's a problem and the committee's not happy, they might make you take another semester. That's the nature of research. Research isn't absolute. It can't be scheduled as well as classes. And so those people tended to go with just doing a certain number of hours. They had to take extra hours instead of doing the thesis, but they were happy with that because they knew when they'd be done. A lot of master's programs do have a written or oral exam. The one I was in didn't. For me, it was the way UT Austin's aerospace department worked, and I've heard this is the way it works in others, is that the only oral exam is to get into the PhD program. You take some master's courses, you want to get into the PhD program, you have both a written and an oral exam to qualify for the PhD program. And if you fail those, then you're out, you leave with a master's degree. If you pass them, then you get into the PhD program, and you can get your PhD. At UT, we had a 50% fail rate on the written exam. And so they didn't just let everybody in. It was pretty scary. But once you're into the PhD program, you're pretty much set. You might have to take some more classes, but then you quickly get into this relationship with an advisor, doing your work, doing your research, start writing your book, because a dissertation is almost a book. And by the time you're done with that, you've become a leading expert, world's leading expert in that area. And you have nothing to fear from your committee at that point because you know more than they do about it. And so pretty much at that point you graduate and start hopefully contributing in that area with a career in that area. As far as some considerations for graduate school, I want to focus more on the master's area. You can do research, very common. I want to make it clear that most graduate students don't pay anything for grad school. There's some, I paid for my first semester because I had saved up money through a co-op program, and I really wanted to do more school. I wanted to go down to UT and help build spacecraft, so that's what I did. And I had a quick they gave me a scholarship that made it so that I was only paying in-state tuition rather than out-of-state tuition, and that was huge. That really lowered the price. And then after that first semester, I got a job teaching, and I taught all the way through graduate school. Once I started teaching, that waived my tuition, in addition to paying me a small stipend, enough to live on. And so at that point, grad school was free from then on. And you're not living a fancy life or anything, but I didn't care back then. I was young. That's a good reason to do it when you're young, when you don't have a lot of financial responsibilities. So teaching's one way. A lot more grad students will do research. A lot of the professors, they need these research assistants in their lab. They will pay your tuition. They will pay you a stipend to be in their lab helping them with their research. And that's great because you're actually getting paid to do your master's thesis, more or less. I mean, the research you're doing for them is probably going to turn into your research that you publish. And so it's a great deal. You're helping out the professor with their grant, and you're getting your own publications out of the deal. So that's a great way to go. One of those two options is the most common, though like the Air Force or a company might just pay you to flat out go to grad school. It's especially like an MBA or whatever, or just something that the company really needs. The company needs you to have more knowledge of a certain, let's say you're an electrical engineer and you need to know more about semiconductors. They might just pay you to go to the local university and study semiconductors at night. That's an option. It is expensive. Grad school is more expensive than undergraduate school. So if you have to pay, it's going to be pricey. Another consideration is the subject matter. Grad school is not the same everywhere. Every grad school is a little different. If you're going into a mechanical engineering school for graduate school and you say, I just want to get a master's in mechanical, that's not enough. You really need to have some kind of a plan. Why are you going to graduate school? What do you want to focus on? You want to pick a school that has the sort of professors and the research that's interesting to you. If you're really interested in automotive, you're going to go to a mechanical department that's got nice connections to the automakers, right? And has a lot of neat testing fields to test out new ideas about vehicles. You're not going to go to just any mechanical engineering department that maybe has no connections to the automotive industry. So that's an example. You want to make sure you pick a grad school that's closely tied into the area where you want to work. When you're getting a PhD, it's crucial to look at the faculty members, especially the one faculty member who's going to be your advisor. That's the most important person at the school for you if you're going to get a PhD. You need to have a connection with that advisor, work closely with that person. That person's going to guide you, keep you from going down dead ends, and get you focused into something that's hot and useful that'll help you launch your career. Location matters a little, but really not as important as you might think. For one thing, you might think it's natural to move through your same school, bachelor's, master's, PhD. Most graduate schools would rather not see that. They like to see spreading of knowledge. If you have all your graduate students are homegrown, then the knowledge there's not this nice community involvement of sharing of ideas. Everyone's got the same ideas, right? But if you bring people from other countries, there's a lot of people from other countries. Graduate school has a wealth of diversity from all these different nationalities. It's fascinating in that way. So you get all these different ideas from other countries, plus just other parts of the country. They do things a little different everywhere in the different bachelor's degrees. So getting everybody from different areas is great, and that's something you should do too. You should plan on getting a bachelor's degree one place and your master's somewhere else if possible. You got 2 names on your resume, and you've got that extra perspective, which is helpful. It might be a little harder. You don't know the system as well when you go to a new place, so there's a little bit of pain there at first, but it's worth it to probably get your master's somewhere other than where you got your bachelor's if possible. Of course, you got to decide which department you want to be in, and the specific department's usually pretty clear-cut, but because you are able to move between departments, then you have some options there. In the last minute or so, I want to say graduate school was just wonderful. I found that it opened my mind, and there's this myth about graduate school I want to address. When you might hear this someday, oh, why do you want to get a master's degree? That's going to make your career options so much more narrow. But actually, a master's degree is totally opposite. A technical master's degree is a great broadening experience. By the end of my master's degree, I felt like I could do any kind of engineering. I got so I could pick up an engineering textbook and read it like it was a history book. If it was an undergraduate engineering book, I could just pick it up and start reading it. I used to spend a I used to spend an hour on one page when I was an undergraduate. What in the world are they doing with all this crazy math? Right? And then by the time I was a graduate student, oh yeah, you know, I could actually fly through that stuff because I'd seen it all before. There's all these connections, these math connections between the different areas of engineering. I'd go to a new engineering subject and I could read that book so fast, so easy, and learn the material. And that's what grad school does for you. It makes you much more powerful technically. A lot of it was the advanced calculus and the math studies that we had to do as part of the aerospace department. And once you get that certain level of math sophistication and physics, basic physics, all these different areas become much easier. So I recommend it if you can swing it. You know, before you are gone too long, you don't want to stay away too long. Pretty quick, get your master's if you can swing it because it's worth it. And that's it for today. Guest speakers for the next 5 weeks. Thanks.